I always quite like this rate of reaction question. It throws even the highest candidates have to think about it as a story that and often get it wrong. But once you get a hang of it, it's perfectly logical, and I think you can do these in quite a straightforward way. You just got to get your head thinking in the right way. So what we're trying to do is basically predict the shape of a graph of a rate of reaction when we've monitored the rate of a chemical reaction. So the graph that's already there shows how quickly carbon dioxide gas is given off. So we've got volume of gas on this axis. So we're monitoring the volume of gas every 30 seconds. So when 50 centimetre cubed of 1 mole per decimetre cubed hydrochloric acid is reacted with an excess calcium carbonate powder. So the acid and the calcium carbonate react, gives off carbon dioxide, and we're collecting that every 30 seconds. And that's our first graph. So down here it then says the experiment was repeated on several occasions, changing only one variable each time. For each different experiment, sketch the likely curve of carbon dioxide produced on the original graph. So we're going to sketch it on here. Now, to do this, we have to remember what needs to happen for a reaction to occur. Okay, first things first. For a reaction to occur, particles must collide. And the second thing for a reaction to occur is the collision must have enough energy. Now, this is important because if we're going to speed up or slow down a rate of reaction, we change one or both of these. Now, if we're changing the number of particles, and that changes the amount of collisions, that's going to have an effect both on the rate, in other words, the gradient of the curve, whether it's steep or shallow, and the final destination, in other words, how much gas is produced. If we start with more particles, we're going to get more gas. That doesn't change that's different to rate, it's a little bit different to rate. If we start with the same amount of particles, we end up with the same amount of gas. If we start with less particles, we end up with less gas. So if the thing we're changing changes the amount of energy, we're not changing the amount of particles, and therefore the destination point must be here. If we make the collisions have more energy, then it'll be faster. If we make the collisions have less energy, it'll be slower, but it must finish there if we're just changing the energy. Okay, let's go through them and hopefully that'll make a bit more sense. So the first one says exactly the same as the original experiment, but 50 centimetre cubed or millilitres. I should really change that to centimetre cubed. It will be centimetre cubed in your book because I'll go back to my office and do that straight away. Exactly the same as the original experiment, but with 50 centimetre cubed of 2 mole per decimetre cubed hydrochloric acid. We're going to label this curve B, and an important point here, the calcium carbonate is still present in excess. So it's exactly the same, but we had 1 mole per decimetre cubed acid here, 2 mole per decimetre cubed acid here, so double the concentration. So does that change the amount of energy of the collisions or the number of particles? Answer, double the concentration is double the number of particles. So if we've got more particles, there's going to be more collisions, it's going to be a faster reaction, so it's got to start steeper. Okay, so the curve was going to be steeper than the original one. Now, because we've got double the number of particles, we're going to get double the number of collisions, we're going to get double the amount of gas, therefore, if that finished there, then this one's going to finish twice as high, roughly about there. So we must finish it off up there. So it'd be 2 marks for this, essentially. One for saying it's steeper, one for getting the destination point, the end point right, if you like, double the amount of gas. So we're going to label that one B. Next one, exactly the same as the original experiment, but 10 degrees hotter. Okay, so it's exactly the same as this one here, A if you like, but 10 degrees hotter. So does that change the number of collisions? Well, yeah, it will actually increase the number of collisions in the particles that are there. But we're not starting with any more particles, are we? The set number of particles we start with is the same. Does it change the energy of the collisions? Oh, yes, that's the main factor. Because the particles are hotter, they move with more energy, therefore they collide with more energy. So it's going to be steeper again. Don't worry about whether it's, just as long as it's steeper than the original one, doesn't matter too much where I'll put it there. So it's going to be steeper, but it's going to finish at the same place because we've got exactly the same number of particles. So it's going to finish early. It's going to be flatter earlier. We'll label that curve C. Next one. Exactly the same as the original experiment, but using calcium carbonate lumps, bigger pieces. Okay, so the calcium carbonate was present in excess. We've still got the same amount of calcium carbonate. So we've got the same number of particles. We've got the same number of particles. We haven't increased the number of particles at all. So the end point must be here. Now, what did we use? We used lumps, bigger pieces. Well, bigger pieces is a smaller surface area So if it's got a smaller surface area, there's less room for collisions to occur on. So that's going to make it slower. So we've got less collisions, therefore slower. And it's going to finish at the same point, so it's going to take longer to get there. Okay, and we're labeling that one. What are we labeling that one? We're labeling that one. Do we say D? We did D. That one's D. Exactly the same as the original experiment, but a catalyst added. So again, we haven't changed the number of particles. So we haven't changed the number of particles, so it must finish at the same point. A catalyst speeds up the reaction. That's its job, speed up a reaction by providing an alternative route. So if it speeds it up, speeding up must be steeper. So essentially it's going to be pretty much exactly the same as curve C. So I'll just make it subtly different, but it doesn't matter whether it's a little bit faster or slower, as long as it's faster than the original one. D. And that's that exercise there. The important point to ask yourself, have you changed the number of particles you start with? If you've got more particles, you get more gas. If you've got less particles, you get less gas. Okay, if you've got the same number of particles, you get the same amount of gas. Then ask yourself, does it speed up the reaction or slow it down? Speed it up, steeper gradient, slow it down, shallower gradient. Final question. If the reaction were taking place on a top pan balance, what change would you notice on the balance? Well, it's giving off a gas. It's giving off a gas. Well, law of conservation of energy says if you're giving off particles, then the mass goes down. What would you notice on the balance display? Answer, it goes down. Faster to start with, because the reaction is fastest at the start, and then decreases with a slower rate. Because as the reactions go on, the particles are used up, so there's less collisions and they slow down. And then decreases with a slower rate. And that's that question done.